Welcome to a journey into one of the most groundbreaking scientific frontiers of our time. Today, we're exploring quantum nanophotonics, a revolutionary field that combines quantum physics with nanoscale photonics to potentially transform computing as we know it. Unlike traditional electronic circuits that use electrons, these systems harness photons, particles of light, to process and transmit information in ways that defy classical physics. Join us as we illuminate the breakthroughs, challenges, and extraordinary potential of this cutting-edge technology that might just redefine what we consider computationally possible. Quantum nanophotonics has been gaining remarkable momentum in recent years, with 2023 marking several critical breakthroughs from research teams at prestigious institutions like MIT, Caltech, and the University of Science and Technology of China. But what exactly makes this field so revolutionary? At its core, quantum nanophotonics studies and manipulates light at the nanoscale in quantum systems. While traditional computing relies on electrons moving through circuits, nanophotonic systems use photons to process and transmit information. When combined with quantum mechanics, these systems offer potential solutions to the decoherence and scalability issues that have long plagued quantum computing development. The most exciting recent advancements involve creating structures at the nanoscale that can trap individual photons and manipulate their quantum states with unprecedented precision, an achievement that was barely conceivable just a decade ago. To understand quantum nanophotonics, we must first grasp the peculiar nature of light itself. At the quantum scale, photons exhibit behaviors that completely defy our everyday understanding of physics. The fundamental principle behind this technology lies in light's dual wave-particle nature, a concept that even perplexed Einstein. Photons can exist in multiple states simultaneously through superposition and can become entangled with other particles, creating instantaneous connections regardless of distance. By engineering structures at the nanoscale, often just hundreds of atoms wide, researchers can control these quantum properties with remarkable precision. These specialized structures include photonic crystals, which create forbidden zones where certain wavelengths of light cannot propagate, plasmonic waveguides that channel light along metal surfaces, and quantum dots that can confine light to volumes significantly smaller than its wavelength. This confinement creates intense light-matter interactions that are essential for quantum information processing. These nanoscale structures effectively become the hardware for manipulating quantum information, creating the building blocks for quantum computers that operate using fundamentally different principles than classical machines. The implications of quantum nanophotonics extend far beyond academic curiosity. This technology promises computing capabilities that could solve problems currently intractable for even our most powerful supercomputers. Imagine molecular simulations that could revolutionize drug discovery by accurately modeling complex protein interactions at the quantum level, potentially reducing pharmaceutical development from decades to years. Or consider optimization problems in logistics that could transform global supply chains, making them vastly more efficient and environmentally friendly. Financial modeling could benefit from quantum algorithms that analyze risk and market behaviors with unprecedented depth. Perhaps most exciting is the potential impact on artificial intelligence, where quantum nanophotonic systems could process neural networks of complexity far beyond today's capabilities, potentially bringing us closer to more generalized AI systems. These aren't just incremental improvements. They represent computational abilities that are qualitatively different from what we can achieve today, opening doors to solutions for some of humanity's most pressing challenges in medicine, climate science, and materials development. One of the most significant challenges in quantum computing has been maintaining quantum coherence, keeping qubits in their delicate quantum states long enough to perform calculations. Traditional approaches require temperatures approaching absolute zero, making quantum computers extremely expensive and impractical for widespread use. In September 2023, researchers at the University of Science and Technology of China achieved a remarkable breakthrough. They developed nanophotonic waveguides that can maintain quantum coherence at temperatures approaching 4 Kelvin. While still very cold, this is significantly warmer than previous systems that required temperatures in the millikelvin range. This achievement came through creating specialized silicon nitride structures with dimensions precisely engineered to trap photons while minimizing their interaction with the surrounding environment. These waveguides, measuring just 220 nanometers in width, about 400 times thinner than a human hair, use what physicists call topological protection to shield quantum states from environmental noise. The significance of this temperature milestone cannot be overstated. Operating at 4 Kelvin instead of millikelvin temperatures means quantum systems could potentially use mechanical cryocoolers rather than expensive and cumbersome liquid helium systems. This shift represents a crucial step toward practical quantum computers that could operate in standard data centers rather than specialized laboratory environments. The USTC team achieved this by exploiting the concept of quantum confinement in their nanophotonic structures, creating protected states where photons become partially isolated from environmental disturbances. Beyond computing, quantum nanophotonics is opening pathways toward something equally revolutionary: a quantum internet. This wouldn't just be a faster version of our current internet, but a fundamentally different network that would use quantum entanglement to enable communications that are secure by the laws of physics themselves. In August 2023, a team at Caltech successfully demonstrated the first nanophotonic quantum repeater, solving a critical challenge for extending quantum communications beyond limited distances. Traditional quantum signals cannot be amplified without destroying their quantum properties, making long-distance quantum communication extremely challenging. The breakthrough device uses nanophotonic cavities, tiny structures that trap light, to temporarily store quantum information and transfer it to new photons. This process, called quantum transduction, was achieved with a remarkable fidelity of 97.4%, far exceeding previous attempts. The repeater uses diamond-based nanophotonic structures containing nitrogen vacancy centers that can interface between stationary and flying qubits. What makes the quantum internet so revolutionary is its approach to security. Rather than relying on mathematical complexity for encryption as current systems do, quantum networks leverage the fundamental laws of physics. When two particles become quantum entangled, measuring one instantaneously affects the other, regardless of the distance separating them. This enables quantum key distribution, where any eavesdropping attempt necessarily disturbs the quantum state and alerts the communicating parties. The Caltech team's quantum repeater effectively functions as a relay station, preserving this quantum information while extending its reach. Their diamond-based platform is particularly promising because diamond can host quantum states that remain coherent at relatively high temperatures, potentially enabling quantum network infrastructure that doesn't require extensive cooling. While much of quantum nanophotonics remains in research laboratories, commercial applications are beginning to materialize at an accelerating pace. Tech giants including IBM and Google, along with specialized companies like PsiQuantum and Xanadu, are investing heavily in photonic quantum computing approaches. PsiQuantum has raised over $665 million in funding and recently announced ambitious plans to deploy its first commercial photonic quantum computer by 2025. What makes their approach particularly promising is that they use silicon photonic chips manufactured in conventional semiconductor facilities, potentially allowing for faster scaling than other quantum technologies. Beyond computing, the industry is increasingly focused on quantum nanophotonic sensors, which can achieve sensitivity levels that are physically impossible with classical devices. These sensors can detect minute changes in electromagnetic fields, gravitational forces, and biological processes with unprecedented precision. In healthcare, early trials are using quantum nanophotonic sensors to detect biomarkers for diseases like cancer at previously undetectable concentrations, potentially revolutionizing early diagnosis. The industrial adoption extends even further. Financial institutions are exploring quantum algorithms for portfolio optimization and risk assessment that could transform investment strategies. Automotive companies are investigating quantum sensors for next-generation navigation systems that don't rely on GPS signals. The energy sector is examining quantum approaches to improve solar cell efficiency and battery chemistry through better understanding of quantum effects in materials. What makes photonic approaches particularly attractive for commercialization is their compatibility with existing manufacturing infrastructure. Unlike some quantum technologies that require entirely new fabrication methods, photonic quantum chips can leverage decades of advances in silicon photonics and semiconductor manufacturing. This compatibility could significantly accelerate the timeline from laboratory demonstration to market deployment, potentially bringing quantum advantages to commercial applications sooner than competing approaches. Despite the remarkable progress, quantum nanophotonics faces significant hurdles before widespread practical implementation becomes reality. The field still contends with three major challenges: scalability, error correction, and developing practical quantum algorithms that can demonstrate clear advantages over classical approaches. Scaling up quantum nanophotonic systems involves maintaining quantum coherence across increasingly complex networks of photons. Each additional qubit exponentially increases the computational power but also the difficulty of maintaining quantum states. Error correction presents another formidable challenge. Quantum states are inherently fragile, and even minor environmental interactions can cause errors. While classical computers can simply copy data to protect against errors, the no-cloning theorem of quantum mechanics prevents direct copying of quantum states. Researchers must develop complex error correction codes that spread quantum information across multiple physical qubits to create more robust logical qubits. One of the most promising aspects of the photonic approach, however, is its potential for room temperature operation. While current systems still require cooling, photons are far less sensitive to thermal noise than electronic qubits. Several research groups have demonstrated quantum effects in nanophotonic systems at temperatures significantly higher than competing technologies, suggesting a path toward quantum devices that could eventually operate in everyday environments without specialized cooling infrastructure. The interdisciplinary nature of quantum nanophotonics, bridging quantum physics, materials science, electrical engineering, and computer science, creates both challenges and opportunities. This convergence of disciplines has accelerated innovation but also requires new educational approaches to train the next generation of quantum engineers who can work across these traditionally separate fields. Universities worldwide are now developing integrated quantum engineering programs to address this need, preparing students for careers in a field that barely existed a decade ago. The holy grail of quantum computing has always been systems that can operate at or near room temperature, eliminating the need for complex cooling infrastructure. While we're not there yet, quantum nanophotonics offers one of the most promising paths toward this goal. Unlike electron-based quantum systems, which are highly susceptible to thermal disruption, photons naturally interact less with their environment. This inherent isolation helps preserve quantum states even at higher temperatures. Recent experiments with specialized nanophotonic cavities have demonstrated quantum coherence at temperatures approaching 77 Kelvin, the temperature of liquid nitrogen, which is far more accessible and economical than the liquid helium temperatures required by many competing technologies. Some theoretical models suggest that with the right combination of materials and topological protection techniques, quantum nanophotonic systems might eventually operate at temperatures above 200 Kelvin, approaching the freezing point of water. This would represent a transformative breakthrough, potentially allowing quantum processors to be cooled using modified versions of conventional refrigeration technology rather than exotic cryogenic systems. The implications would be profound. Quantum computers could move from specialized research facilities into standard data centers or even local servers, dramatically accelerating their adoption and application. Materials science plays a crucial role in this temperature challenge. Researchers are exploring exotic materials like silicon carbide, hexagonal boron nitride, and various two-dimensional materials that can host quantum emitters with exceptional stability at higher temperatures. By precisely engineering the interaction between these materials and nanophotonic structures, scientists aim to create protected quantum states that remain coherent despite thermal fluctuations in their environment. Perhaps one of the most exciting potential applications of quantum nanophotonics lies at the intersection with artificial intelligence. Current AI systems, despite their impressive capabilities, are fundamentally limited by classical computing architectures. Quantum nanophotonic systems could potentially process neural networks of vastly greater complexity and with different operational principles than today's AI. Quantum neural networks, running on nanophotonic hardware, could exploit quantum superposition to evaluate multiple potential solutions simultaneously, potentially allowing AI systems to solve currently intractable problems in optimization, pattern recognition, and creative generation. Several research groups are exploring how quantum properties like entanglement could create entirely new types of neural connections that have no classical equivalent. These quantum neural networks wouldn't just be faster versions of classical systems, they would represent a qualitatively different approach to machine learning. Early experiments in quantum machine learning have already demonstrated advantages for certain specific problems. For instance, quantum systems can perform feature mapping into higher dimensional spaces more efficiently than classical computers, potentially improving classification tasks. Quantum nanophotonic implementations are particularly promising for these applications because they can process multiple quantum bits in parallel through different wavelengths of light, creating highly efficient quantum neural network layers. The integration of quantum nanophotonics with AI could lead to systems capable of discovering new materials, medications, or solving complex societal challenges like climate modeling with unprecedented effectiveness. This convergence represents not just an evolution in computing but potentially a fundamentally new approach to machine intelligence. A global race is underway to achieve what scientists call quantum advantage, the point at which quantum computers can solve problems that are practically impossible for classical supercomputers. Nations and corporations worldwide are investing billions in quantum technologies, with quantum nanophotonics emerging as a leading contender. China has made quantum technology a key priority in its latest 5-year plan, with massive investments in both basic research and technology development. The European Union has launched a €1 billion quantum flagship program with significant focus on photonic approaches. In the United States, the National Quantum Initiative has allocated over $1.2 billion to accelerate quantum research and development. Private investment has been equally impressive. Beyond established tech giants, venture capital has poured into quantum startups, with photonic approaches attracting particular interest due to their potential scalability. PsiQuantum's remarkable $665 million funding round signals the market's confidence in photonic approaches to quantum computing. This global competition has accelerated progress but also raised concerns about a quantum divide between nations with advanced quantum capabilities and those without. Some experts argue that quantum technologies should be developed with international cooperation to ensure their benefits are widely shared, while others emphasize national security implications that drive competition. What's clear is that the first countries and companies to achieve practical quantum advantage will gain significant economic and strategic benefits, potentially reshaping global technology leadership. The race extends beyond just building quantum computers to developing the algorithms, applications, and quantum-trained workforce needed to fully leverage these revolutionary systems. As quantum nanophotonics advances toward practical implementation, important ethical and security questions are emerging that demand careful consideration. Perhaps most pressing is the impact on cryptography. Many of today's encryption systems that protect everything from financial transactions to personal communications rely on mathematical problems that are difficult for classical computers but could be easily solved by quantum computers. This has sparked urgent development of post-quantum cryptography, encryption methods that would remain secure even against quantum attacks. The National Institute of Standards and Technology is already in the final stages of standardizing new cryptographic approaches designed to withstand quantum attacks. Beyond encryption, quantum technologies raise profound questions about privacy, security, and the balance of power between individuals, corporations, and governments. Who will have access to quantum computing capabilities? How will we ensure these powerful technologies are used responsibly? Will quantum advantages exacerbate existing digital divides or create new ones? The dual-use nature of quantum technologies also presents challenges. The same quantum sensors that could revolutionize medical diagnostics could potentially be used for surveillance. Quantum communications systems that provide perfect security for legitimate users could also protect malicious communications. These ethical considerations have prompted calls for developing international governance frameworks for quantum technologies before they reach widespread deployment. Some researchers advocate for responsible quantum innovation approaches that consider societal implications throughout the development process rather than as an afterthought. As quantum nanophotonics moves from laboratories toward practical applications, addressing these ethical and security implications becomes increasingly urgent. As we look toward the horizon of quantum nanophotonics, we can begin to envision a future where quantum technologies are seamlessly integrated into our technological infrastructure. Within the next decade, we may see the first quantum computers based on nanophotonic principles achieving practical quantum advantage for specific applications like drug discovery, materials science, and financial modeling. These early systems will likely be hybrid quantum classical architectures, with quantum processors handling specific computationally intensive tasks while classical systems manage the overall workflow. By the 2030s, if current progress continues, we might expect more general-purpose quantum computers with thousands of logical qubits, capable of tackling a wider range of problems with quantum algorithms that are still being developed today. The quantum internet may begin to take shape, initially connecting research institutions and critical infrastructure with unhackable quantum communications, before gradually expanding to more general use. Quantum sensors based on nanophotonic principles could become commonplace in healthcare, environmental monitoring, and navigation systems, operating with precision far beyond today's capabilities. Perhaps most exciting is the potential for entirely new applications that we cannot yet envision. Just as the classical computer evolved from specialized scientific equipment to the ubiquitous, multi-purpose devices we use today, quantum technologies may follow a similar but accelerated path of evolution and integration into daily life. As quantum nanophotonics advances, it represents not just an evolution in computing but potentially a fundamentally new approach to information processing that harnesses the strange properties of quantum mechanics using the most elusive and fastest particles in the universe, photons. The coming decade will likely determine whether these tiny light-based systems will trigger the computing revolution many scientists anticipate, potentially redefining what we consider computationally possible. Quantum nanophotonics stands at the frontier of human innovation, merging the quantum realm with our mastery of light to potentially revolutionize how we process information. From the groundbreaking temperature advancements at USTC that bring quantum computing closer to practical implementation, to Caltech's quantum repeaters paving the way for a quantum internet, we're witnessing the birth of technologies that could reshape our computational capabilities. The commercial landscape is already transforming, with companies like PsiQuantum raising hundreds of millions to bring photonic quantum computers to market. Yet significant challenges remain in scalability, error correction, and algorithm development before the full potential of these systems can be realized. As researchers push toward room temperature quantum operations and explore applications in artificial intelligence, a global race accelerates to achieve quantum advantage. This revolution carries profound implications for security, ethics, and the balance of technological power. The quantum future being built today through nanophotonic innovations may soon redefine what we consider computationally possible, solving problems that have long remained beyond our reach and opening doors to discoveries we cannot yet imagine. The light-based quantum revolution isn't just coming, its first beams are already illuminating our technological horizon. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.